In this video, we're going to look at the statics of rigid bodies in mechanics for A-level maths. So let's take the first example. A uniform rod AB of mass 40 kilograms and length 10 meters rests with the end A on a rough horizontal ground. The rod rests against a smooth peg C where AC equals 8 meters. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. Find the magnitude of the reaction at C. Hence, find the coefficient of friction between the rod and the ground. So the first thing we ought to do in mechanics is to draw a clear diagram. So here's the rod, here's the ground. It's rough, so let's illustrate that by drawing some lines to illustrate that it's rough here. So this is all rough. And then we need to mark in our forces. So we have a normal reaction here, R, and we also have a normal reaction like this, which is at 90 degrees to the rod, because it's the peg that touches it. So I'm going to draw that, and I'm going to mark in 90 degrees to show we've got a right angle there. Then we also know it's inclined at 15 degrees to the horizontal. So let's draw in 15 degrees. And we also know that it's rough. So this force here is friction. So we're going to write mu R, or F equals mu R. I'm just going to write mu R in this video. Now, the weight of this rod is 40 G, mass times gravitational force. So when we take moments, every force must be perpendicular to the distance, or the distance must be perpendicular to the force. So we must have it in that way before we can take moments. So the normal reaction coming from the peg C, I want to note this is C, is perpendicular to the rod. That's not a problem. What we need to do is to resolve the weight. So we're going to resolve that. So here, and then we're going to draw the other components here, going down. Okay, so we get a 90-degree right angle triangle there. So normally we'd resolve both, we can have both components. Okay, so I'm going to, for the sake of this video, I'm going to write both in, but the only component we need is the ones that are perpendicular to the rod. So this is going to be 15 degrees. So it's going to be 40 G cos 15, and this would be 40 G sine 15, but we don't really care about this, the 40 G sine 15, because that's not perpendicular to the rod. So what is perpendicular is this force, which I'm doing in purple here. That's what we care about. Okay, the purple force, because that's exactly perpendicular to the rod that we have. So we now need to write in our lengths of the rod. Now, if the rod is 10 meters, the weight acts in the middle of the rod because it's uniform. So we can mark that as 5 meters. That means the other one is 5 meters as well, from the midpoint to the end of the rod. But AC is 8 meters, meaning the distance here must be 3 meters. So let's mark that in. So 5 plus 3 is definitely 8. So because it's 10 altogether, implies that the last part here is 2 meters. So we've been told that this is point B. Right, so now that we've got all our lengths in, we can now take moments about A. Why do we take moments about A? We take moments about A because that means when we take moments about A is a pivot, and the force, the normal reaction R, and the frictional force will not count. So That's good, they're eliminated. So we're going to take moments about A. This means in a clockwise direction. Well, it means the purple force here, 40G cos 15, that's the one that's perpendicular to the rod. That's going to turn clockwise by a distance of 5 meters towards A. So that's going to be our clockwise moment. So that's going to be 40G cos 15 multiplied by the perpendicular distance towards A, which is 5. Now that must be equal to the anti-clockwise moments. Well, the anti-clockwise moment is going to be n, so that's perpendicular towards the rod, so that's going to be n times by 8, so equals to 8n, so I can write that here, equals 8n. So therefore n is simply 40G cos 15 times 5, all divided by 8. And we're going to work this out on a calculator. Now that works out to be the following value, 236. Now I'm going to write the full value out, otherwise we'll get inaccuracies in further calculations. So I'm going to write the full calculator display out because we may need it later on. Okay, so we get 236.65 and so on. Now, that's the normal reaction at C. So A level, like GCSE, we round all answers to 3SF. So that's 237 newtons rounded to 3SF. But we got the true value for later calculations. So we can go back to our diagram and say, right, so what we need to do now is to resolve the normal reaction, because we need to now resolve horizontally and vertically. So what happens is, the way I explain this to students is we're going to draw in a horizontal at n, okay? And this is more for your understanding. So we have an alternate angle here, is 15. And what we're going to do, we're going to resolve this triangle. So we've got that going here. So we've got that over here. And then when it's slightly smaller. And then we're going to resolve towards the right here. To make that a bit more precise, like that. So we've got a triangle here, so right angle, and we can say that this angle, well, if all of that is 90, that's going to be 75, so therefore this is going to be 15 as well. So this angle is 15 degrees, meaning this component is going to be n cos 15, and this component here is n sine 15 respectively. So we now got our components. It's in the vertical component and the horizontal component. So now what we do is we're going to resolve horizontally and vertically. So for part B, we resolve vertically first. And if we were to do that, we can see R plus n cos 15. So we're going to do that. So R plus n cos 15. Now that is equal to the force that's coming down, that's 40G. So 40G. But we know what n is, so therefore R is 40G minus n cos 15. We've worked out n previously, so we're now going to get R is 40G minus 236.6 and so on times cos 15. I've got the true value, so I can type it in. We're going to write the true value for R. So let's do that. So that works out to be, on my calculator, 163 0.4118888. Okay, now if we resolve vertically, we can now see from our force diagram that the frictional force going towards the right, mu r, is now equal to n sine 15. So let's do that. So I'll put the diagram again. The horizontal force, mu r, is now exactly equal to n sine 15. So let's write that down. So mu r is equal to n sine 15. So in our case, mu times 163.411 and so on is equal to 236.6 and so on sine 15. So therefore mu is 236.6. I've used ellipses because I'm going to use the true value from before my calculator, times sine 15, all divided by the true value of r, which is 163.41 and so on. We're going to write the true value of mu down and then round it to 3SF as we always do. So let's do that. So on my calculator, it gives me the following value. It gives me 0.74819.731. Therefore, mu is 0.374, correct to 3 significant. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So if we take this question here, we've got a uniform rod with a weight of 80 newtons. So I'm going to elongate the weight slightly longer. Here, 80 newtons, like so. We've got mu r, the frictional force going towards the right, the normal reaction at A, the tension in the string T, and then now we need to resolve. So resolving this here, we know this is 30 degrees. This is 80 cos 30. And then the one that we don't really require relative for completion is going to be parallel to the rod, which is going to be 80 sine 30, but that's redundant. We don't really need that here. I've just done that for completion. We need the pink one, which is perpendicular to the rod. I'm going to draw that a bit more realistic. So it's making sure it's perpendicular here. So that, and then we've got that here. We should do it in purple. So we've got that here. So we get a nice right angle triangle. This is 30. Hence this is 80 cos 30. And in purple, we're just going to write that in here, 80 sine 30. We don't really need the purple one here. We need the one that's perpendicular to the rod, which is 80 cos 30. So now what we can do is we can take moments about A. So let's take moments about A here, taking clockwise as positive. So 80 cos 30, that's going to go clockwise. So it's, and we also need the lengths as well. So we're going to call this A to the midpoint of the rod here, and that's also likewise going to be A. So we're assuming that the length of the rod is 2A. So what we're going to do here is taking the clockwise moment, which is 80 cos 30 times by the distance. So don't forget the force is perpendicular to the rod. So force times perpendicular distance towards A, which is A. Now that's going to be equal to the anti-clockwise moment, which is 2A times T. Now the A's will cancel out, so we can cross those out. They're gone. So to find T, we're just going to divide it all by 2. So T equals 80 cos 30, all divided by 2. So I'm just going to write that as 40 cos 30. Now they do ask us to work out the value of that. So I'm going to write the true value out for T because they asked us for the magnitude of T. So let's get our calculator. Let's type that in. So I get, from my calculator, I get 34.64101.615. Let's make the 4 a bit more clearer here. So we need the true value for T, maybe in a further calculation. So because I want all of these forces, so we can round T for the 3SF, but using the true value in subsequent calculations. So T is 34.6, correct to 3 significant figures. Now, then what they want is the normal reaction. So what we need to do here, like what we did in the previous example, is we need to resolve this. So we have a horizontal here. I showed you in the previous example, that's 30. So we can resolve this like so. That's also going to be 30 here. So the one that contains the angle is cos, so it's T cos 30. And that's T sine 30. So we've resolved our components there. So we can go ahead and say that R plus T cos 30. So I'll just make the upward arrow a little bit clearer there. So it's like this and that. So that there and across. So it's T cos 30 plus R. So let's do that. So resolving vertically upwards, we've got R plus T cos 30 equals the force coming down, which is 80. So R is 80 minus T cos 30. So R is 80 minus 34.6 and so on times cos 30. And that gives me exactly 50 newtons by using the true value of T. So I get 50 newtons for R. Prove the clarity of my handwriting there. And then to find mu, we need to now resolve horizontally. So resolving horizontally towards the right. So going back to our diagram here, so we can see that the force that's going towards the right is mu R, and the force going towards the left horizontally is T sine 30. So therefore we can say mu R is T sine 30. Mu is T sine 30 divided by R, and hence we have to use the true values here. So that's going to be mu is 34.6 and so on, sine 30, all divided by 50. And then we can see that mu works out to be 0. I'm writing the full value and then I'm going to round to 3SF. 0.346 410 0.1615. So therefore mu is 0.346, correct to 3 significant figures. And that's been rounded to 3 significant figures.